So, read those 9 pages. Pretty chill. Got like days and days to do that. And then, maybe make some notes to yourself to help you. And then there's going to be a quiz on Monday. And what I need are, so we're doing a math class, right? It's a 400 level math class. Kayla's cracking up. Definitions are absolutely key, and they're precise. So we want precise definitions. That's what we're shooting for. So the definitions that are in the book, those are the ones I want. Right? There's only one other expert on this stuff maybe in this room, and I'm barely an expert. And I won't make up the definitions myself. I'll use theirs. So let's all use theirs. So to see that we can, and this will of course be closed book, quiz, define. Give me the definitions for isometry. Let's try that one again. Symmetry. Also, those are in the previous section. You won't find those in those. You'll have to look back because they were on the last quiz. Geodesics.
I can do that one right now.
Six. Intrinsic versus extrinsic. And then I've got a theorem that I want you to state. You don't have to prove it because we're going to work on proving it on Monday together. We're going to do the proof together. But I want you to have it ingrained in your mind. So define these, state perfectly with words exactly from the book and the picture from the book. I'm going to do it right up here. State perfectly. The vertical angle theorem. It's actually a really basic result. It's almost common sense in a way when you see it. So the VAT says the following. I hate this red. I'm not a fan of this red. Let's try this black. This board is very weird about pens that I use. So first off, there's a picture, and it's 2 lines crossing with an alpha and a beta inside there. What do you think is true about those 2 angles?
The same.
Same angle. That's the theorem. But we're going to say it like it says in the book. We're not going to write, they're the same. That's not a statement of the theorem. So what we will say is, opposite angles formed by 2 intersecting lines, intersecting straight lines are congruent. And you already know this. You knew that intuitively, so that's awesome. But that's the statement I'll be looking for. Any deviation from said statement will lose said points. What's the definition of isometry? What's the actual definition? There was parts, like some of you had some of it. And some of you had it, but you used your own words.
Wow.
Yeah. What's isometry?
A transformation that perhaps the shape and the angle and distance?
Yes, a transformation that preserves angles and distances. That's it. Shape is a vague word. We want angles and distances. What is a symmetry? What is a symmetry? So, symmetry is defined in terms of isometry. What is a symmetry?
Isometry of a region in space that takes some figure of itself.
Yes, It is an isometry that takes a figure in space back onto itself. Yes, good. So that's a symmetry. These words you'll have to look up, but you will find them in the reading. And then there will be bonus questions that will come from the reading. Maybe a picture by the words. Who can say? But it shouldn't be mysterious anymore where all these questions are coming from. So let's just do me a favor, just ace this. Just please, for the love of all that's holy, just get 100% on this. And then if you get the extra credit, you'll get over. There was actually 14 points possible on that quiz you just got back. The extra credits were 2 each. Yeah. Any questions, my friend? Friends. You are a friend as a unit, one whole friend.
Yeah, could you,
Yes, sir.
like, maybe with some figure, could you like visually define a symmetry? Like, because like when I use the word isometry in the definition of a symmetry, I don't really understand what it means.
Yes.
Isometry on its own is fine, but not when it's like described, because it like, okay, it says, it's an isometry of a region of space that takes the figure onto itself.
Absolutely.
I don't know what that means.
Okay.
Or what it looks like.
Gotcha. So let's take a look. I gotta try to make I'm just gonna make an equilateral triangle. So here's an equilateral triangle, theoretically an equilateral triangle, okay? Here's the center of the equilateral triangle. So imagine a pivot point that I can spin it around on. So, an isometry, so remember isometry equals a transformation. So that could be a scaling, or a rotation, or a shifting. Those are the basic ones, or a flip.
A flip, yeah.
Flips as well, flips change orientation. So transformation that maps that preserves angles and distances. So I actually just gave an example that wasn't an isometry. Which one of those things I said is not an isometry?
Oh, a scale.
The scaling. So scaling's not an isometry because it does change distances. So we're just talking about rotating the plane, flipping the plane, translating. Those are the three basic operations in the plane that preserve things. So here, an isometry of this is a rotation by 120 degrees.
About exactly.
About the center. So if I took this and I rotate by 120 degrees about the point P, I'm making up some notation here, but
Yeah.
that is an isometry, and that is a symmetry. So this thing has a rotational symmetry. Lots of different kinds of symmetry, and they're based on the transformation that was used as well. This has a flip symmetry, a mirror symmetry, because I could flip it over that line and it lands back on itself. Does that make sense? It does not have a translational symmetry, because if I shift it in any direction, it won't land back on itself. Whereas something like this, if I think about, let's just take a line and do something to it, like this, and imagine this continuing on forever in both directions. So this has a translational symmetry.
Because on the like further down, it's the same as it is further.
Yeah, because I just shift this to here,
Yeah.
just do a shift, translate by that amount, and it's back on
Sine
itself.
and Cosines are translational.
Yeah, exactly, yeah. It might also have a half-turn symmetry. That was another one we talked about, right? So this has a half-turn symmetry about that point. If I flip it, it's back on itself. And half-turns are also, that's like rotation by 180, so it's just a rotational symmetry. Does that help?
Yeah, but the symmetry portion of
Yes.
isometric. So like when a region of space takes the figure onto itself. So that's in the definition of symmetry.
Yes.
Right? So like what is that? Like how could you show that with that equilateral
So
Because like,
here,
okay, so like, all right, if you were to flip that about point P, it's an isometry, right?
An-
Because that's a transformation. If you were to transform this in any way, that would be like an isometry of the
an
original.
isometry. Yeah, I see what you got. You're like combining the words sometry and symmetry, so I was like trying to figure
how,
out
How do I say?
isometry,
Isometry.
isometry, and symmetry.
Yeah.
So, but they're
And
very
then
similar.
the definition of symmetry uses isometry in its
Yes.
definition.
So, yes. So a symmetry is an is an isometry
Yeah.
is a translation, a flip, or a rotation
Okay.
takes a figure and puts it back onto itself so you couldn't tell anything changed. So it lands back onto itself.
Right. So if you rotated that 120 degrees about P, it would still look like the same
That's right.
figure.
That's right.
And then, is that a symmetry?
That is a symmetry, yes. So this has a rotational symmetry.
Are they even independent of each other?
Yes. Isometries are used as part of defining symmetries, but I could take a figure like this, take this, and this actually, unfortunately, I'll do some weird shit to it. Make it like that, it's got some weird stuff in it. So that figure right there looks kind of cool, but it doesn't really have any symmetries because there's no way I can translate it or flip it.
There's no symmetries?
There's no symmetries in this
Okay.
because there's no isometry that maps it back onto itself besides just leave it alone.
Right.
So I can't move this and have it somehow look the same as it did before I moved it. So it's kind of, think this, maybe I said like this, invariance under translation, rotation, or flips. Does that make sense?
It does, but it only makes sense if like they're not independent of each other.
I'm
Like,
not
how
sure,
can you have
explain
it?
to
How
me
would
what
you have
mean
an
by that?
isometry without symmetry, and vice versa?
So an isometry would be, if I took this figure and I had it maybe over here. I don't know. I'm sure. Just imagine this is the same damn thing.
Yeah.
Okay.
Gotcha.
So an isometry here would be translate and rotate, and that maps that onto here. So an isometry is just talking about moving things in the plane in a certain way.
And then the
Pushing,
symmetry is
rotating. And sometimes that
Results in
reveals
asymmetry.
asymmetry, but
Uh-huh.
not always.
I see.
Does that?
I see.
So is an isometry something like a half turn or a reflection line, and any of those
Yes.
is a type of isometry, and that can reflect symmetry or not?
Yes. Absolutely. We got these. So if you came in late, here's your assignment for Monday. We're having a quiz again. We're going to do better on the quiz.
Yes.
Because what we're going to do, if you miss this, is we're going to learn the definitions in the book
Yeah.
and remember them.
Remember them.
How do you study for a quiz like this?
Flashcards.
Flashcards are cool. Oh, flashcards are cool. I like that. That's old school.
Very.
How else could we study for a quiz like this? What's Alexander?
I just have hot takes. It's okay. I have no techniques.
What's your hot take?
No technique.
Alexander's hot take number 1.
Jarvis.
It's okay. Moving forward. Next question.
Okay, yeah, the people are unsubscribing from this channel right now as we talk. All right. So, what I would do, are you okay?
Yeah.
All right, I'm just giving you shit.
I know.
All right. What I would do is write these words down, write the definition from the book next to them, and then do that again without the book. Do I really need to be telling you this stuff? Like, we're all like in a 400 level math class, right? Like, I'm just telling you to remember words. So these are the words I need you to remember for Monday. And if you came in late, you also need to state perfectly the vertical angle theorem. You do not need to prove it, but it'll be part of this reading that you need to do. And we will prove it together on Monday. Okay, so I think I've said the start of the class 6 to 8 times already. So we're gonna move on. So you have some homework for me. You have an assignment that was due. I will collect that. Thank you. Beautiful. Thank you. Oh,
I'm gonna be so honest, I did it like a lot of my can I take a picture of this and send it to you?
yes, but I did ask for like
Yeah,
a
I
write-up
have
of
like
those.
a little bit of it.
What?
Part B on this.
Yeah, it's gonna be 10-10, bro. If this isn't a 10-10, I swear it's
Write
my
it up,
last
can you put it
one.
in?
I'm out.
Yes.
Okay, so,
I'm having like the worst time, so
okay, okay, are you all right? Kind of not, okay, all right. And Evan's cleaning that up for
I
me.
have to give you these, I only.
No, you keep your spheres. Those spheres are yours
I drew on my sphere.
to keep forever. I hope you also can erase from your sphere.
I already erased from it.
I hope Kayla can erase from her sphere, because she's got some hardcore shit on that sphere.
It's wet erase markers.
Oh, awesome. Cool. Thank you.
These are our sphere.
And then,
This is the world that I
one day,
It's about this
we'll
size.
see the other people in this class, people who are watching this. One day we'll see you. One day next week, hopefully. And you still owe me that shit today. Alright, so, enough said. So, alright, I've got some notes here for myself. I think I've ranted and raved a lot. Tell me, sphere work. So hopefully you did some sphere work over the weekend. And that's what, yeah, that's it. Got a light bulb idea, right? Like, brilliant. Like one of those sweet ass expensive light bulbs. So, could you take a minute while just on your own? And I'm going to ask you a couple of questions, and hopefully you can kind of think about the experiments you did and what you just wrote up and gave to me. And I just want you to answer these on your own, so it's a meditative, private moment with you and your brain. And that can be of varying qualities and pleasantness. If I can find a freaking eraser.
What side of your eye?
What's that?
Side of your eye?
My. Can anybody help me find an eraser, please?
Oh, you could have picked a towel. I don't know.
Just call. Why don't you just call security and tell them there's a lost homeless man wandering around looking for an eraser.
Let's see one.
He seems like he's dehydrated. Like, what the fuck? I had an eraser just a bit ago. I erased this board. It must be in here somewhere. Oh. There we go. Oh my god, that homeless man's our professor. He still looks dehydrated. Skin's all shrivelly. Alright. So, here's the questions I'd like you to contemplate for a short period of time. What are the lines on a sphere? What is straight?
How many times are you gonna ask us what's straight, Dr. T?
What's this?
How many times are you gonna ask us what is straight?
Many freaking times on a sphere. Which is, these are actually kind of the same question, I guess.
Oh.
And why? But why? That part. Try to express that part. Based upon just some of the stuff you did. And there was 3 experiments. Let me kind of help you. There's 3 experiments that you were supposed to do. There was the rubber band experiment. Does that make sense?
Yep.
Yes.
Yeah, cool. And then there was
Chalk.
the rolling it on a straight line experiment. I don't know if anybody did that one. I'm kind of curious, like how these went. Roll on a line. And then the third one was the ribbon test. Strip of paper or something like that. So take a minute, express yourself. That, because this class is about that. Try to write out our ideas and formulate them better.
cut this one long.
I like that you're just never letting go of your sphere.
I'm thinking.
Comfort
I'm
sphere.
meditating.
Oh, cool, awesome.
Don't you know? I'm connecting.
I do now.
It's called
Makes sense.
sphereful mindfulness.
Yeah, I like it. Absolutely.
Connecting with the sphere.
Freaking love these spheres. Sure. Yeah. Oh, that looks so good. Look at that. Alrighty. Anyone care to share? Alexander, you're very stoked. Tell us something.
I mean, if anyone else would like to go, please
Penelope, were you gonna say something?
take the stage.
Yeah.
Go.
Penelope's gonna say something.
You go. Sorry. Sorry, I kind of thought of it in the sense of like how you define a circle walking on the first day of class, and then I used the ribbon example. So if the right side of the ribbon and the left side of the ribbon don't touch both sides, like on the sphere, then one is taking more steps than the other, and we're making a circle and not a straight line.
Yeah, so what do you mean not touch? So you're this totally the right way of thinking.
Yeah.
So
So if like the left side is touching, if we had it perfectly like on the sphere,
yeah.
then the right side wouldn't touch the sphere, thus meaning that the left side or the right side is taking less steps than the right side, creating the definition of a circle that we made on the first day of class.
Yeah.
So that's why in order for something to be straight on a sphere, it has to go through the like center point of the sphere. If a circle was to be drawn around the whole
Yeah.
circle, then it has to, if that was to become a plane, it has to go through
Yeah,
that center
that's
point.
nice. So it has to be a circle that's formed by intersecting the sphere through its center with a plane. That's
Yes.
nice.
Alexander.
Yes,
Straight
Alexander.
line on a sphere is a geodesic, or a great circle.
Yeah. What does a geodesic mean?
It is a, well, it's actually, it's that, it's it's a circle around a sphere, like relative to its starting point that goes through the center. And so if you wanted to walk in a straight line on a sphere, you would have to walk on one of the great circles, which would be like the distance between any 2 points on a sphere from your position lies on a great circle.
Great circle. That's awesome. So that term, great circle, is what we're looking for. And that's exactly what Penelope described. Lou, did you want to add something
Well,
to this?
I don't know if this is like true, but I said that the difference between lines on a sphere and lines on a plane is that lines on a sphere are cyclical, and so you can travel the line is finite, but you can travel infinitely on it.
Yeah,
As opposed
definitely.
to like a plane where I don't know, it has like a
You just keep on going.
Yeah, you just
Yeah.
keep on going without like returning back to any
100%.
coordinate you previously were at.
Yeah, absolutely. What about this? So there's my sphere. Oh. What's that?
The Death Star.
It is. It is.
That is
What's that on a sphere?
what do they call that? A concave?
Is it straight?
Okay.
No, it is not,
How do I know it's not straight?
because it doesn't go through the circumference of the.
So let's pull back. So we're not going to use it's not the intersection of a plane through the center, definitely, right? It's kind of like skimming along. It's like a plane that's cutting
It's a level curve.
At some point, it's like a level curve. Yes, it's a level curve. Yeah, absolutely. Good Calc 3 shit. Nice. So, I want to go back to this idea that Penelope brought up about the ribbon test. So let's talk about that ribbon test and the symmetry. So first off, I think we're all in agreement that these great circles, the lines of longitude on the globe, those are our lines. And they don't necessarily have to be just the lines of longitude, right? These can exist anywhere on the sphere. But it's the biggest circles that are available on the sphere.
Just to
Yes.
make sure I
Yeah.
understand this right, all the longitude lines would be great circles, but
Absolutely.
the latitude lines would not be great circles because if you cut it like the rubber band test, it'll
Yes.
pop off.
Except for one.
Or
and
the
which-
equator.
The equator, yeah, absolutely. Yeah, and that rubber band test is so great, right? Because that rubber band wants to get smaller. And it wants to shrink and it wants to compress. So when you put a rubber band on the sphere just on this little side here, it's just gonna pull that way. And it only is at perfect equilibrium when it's on one of these great circles and the forces this way equal the forces this way. So it's that sense of balance, just like if I took, and I wish I would have brought a little ribbon. Why don't I use one of the people who didn't show up's homework? I need a ribbon. Does anybody have like a cool ribbon?
You can steal your shoelace.
She had ribbons in her long brown hair. No? Okay. Alright, so.
Penelope.
Oh,
is it
yeah!
the right side?
You could potentially have
Oh
ribbons in
wait,
your
I
hair.
do have a
indeed.
ribbon.
That's
That's
more
a
of
more of a
it's a
rubber band.
band.
So,
Yeah, I need something flat.
yeah.
So when we do the ribbon test, on a great circle, the ribbon has a symmetry in terms of how far it is from the circle on either side, right? Because you take a piece of paper and you wrap it on here, and there's gonna be this part, this is super shitty, but there's gonna be this part that's above the sphere. When you're on a great circle, in the center, you've got a symmetry between this side and how far off from the sphere you are. Does that make sense? If you did that ribbon test, you know what I'm talking about. That if the side view, so like from the side view, it's like this. The paper's sitting perfectly same distance off either side. When you're on a great circle that kind of comes down like this. So this is like the front view. The ribbon's coming out this way, like this. When I'm on one of these guys and I try to put the paper or the ribbon on it, so let's do this. So let's say I've got this and this. What I'm going to see is that thing's going to be tangent there, and it's going to be tangent there. And I've kind of got this cone effect going on everywhere except on the great circles. So there's a lack of symmetry here in terms of the angle. This angle is up more than this angle is down here. There's a slant to it. Everywhere except on great circles. And in fact, if I kept extending this thing, it would turn into a cone.
Postulate
It's, what's that?
number 5.
Yeah, we're not there yet. You're right. I see why you're thinking, but those aren't our lines. So this won't be our lines on our sphere, though, right? The lines on the sphere are the big
Oh,
circles.
right.
Yeah, you're looking extrinsically. We're thinking intrinsically. Yes, Alexander.
Okay, if you're, well, okay, so that thing you have drawn right there, the desktop, right?
This one or the other
the
one?
middle one, the middle circle, first figure you
This
drew,
guy,
where the
yeah, yeah.
circle's like on like,
Yeah.
you know, you're on like this, right?
Yes.
Okay, so here's how I like understand these great circles. If you were to make a point, if you were to have 2 points on well, actually that's a bad example. Let me say it this way. If you were to start at one point on a sphere and walk in a straight line and you ended up exactly back at point A, for example. No, I'm just saying like if you were to walk all the way in a circle, right? You've now walked a straight line on a curved surface. Correct?
But I could land back there not walking straight as well, right? Because I could do.
But if you took the shortest path from point A to point A, then you would lie on a great circle.
Well, I don't know about
Take the
that.
longest path.
Give me 2 points.
Because anytime you deviate, okay, so if you, okay, right, say you go from point A to point B, right?
Yes.
And it's not directly 100, you don't draw I don't know how to say this, but a line from point A to point B, and you take any deviation, then you're no longer on a great
Correct.
circle, right?
Correct.
But what if that, right, alright, so.
Yeah,
I'm
gotta
saying
travel
if you
on the
have-
great circle
If you
through
have
those
this
two.
cut, though, if you're starting here, and you're like a human on Earth, for example, right?
Yeah, okay.
And you travel this you're not traveling on a great circle right here because it's not going through the center point, right?
Right.
But you're traveling in a straight line. But you can't travel in a straight line unless it's a geodesic.
That's right. That's right.
But this isn't a geodesic though, do you see what I'm saying?
It isn't, you're right. But it's not the shortest path either. We haven't talked about how to measure distance on the sphere, so let's hold
But
off
I'm
on
just
that.
trying to understand like how you can, if you travel between any 2 points
Uh-huh.
and in a straight line, then you're on a great circle.
Right.
But if you travel, if you're like off-centered on the sphere, then you can't be on like the rubber band, for example, right? If you're like just traveling this
Yes.
cutout.
Think geodesic is what is considered straight as if you lived on the surface.
Okay,
Don't
so,
think shortest distance.
so relative to the person.
Yes. Oh, let me see, hold on, let me get Kayla and then Penel.
Well, I know you said like not to talk about distance, but I think the way that I was thinking about it is like if we're on point A to point B, the shortest distance between those two will like it falls along the great circle, but if you go from like A and then back around to A, it's the longest distance. is the
Yeah,
great circle.
yeah, that's true, yes, but yes, 100%.
So, like what Kayla was saying, is like in order to get to point A to point B, you have to travel the circumference of the whole circle, basically, in order to get back to it, and be on a great circle at the same time.
Yes.
Okay, and then kind of like how you were saying perspective, if we were a bug, or like if we're looking at something like this, I guess, something that's round, it's like perspective, because then everything has a tangent and
Yes,
stuff like that. So, same thing with the great circle, it's perspective based on where you start.
yes,
Okay.
yes. And I want to talk about the distance thing here too, because I think that's how you were thinking, Alexander, in a way. I think you were thinking about geodesics this way. So if I travel a straight line from A to B, I'm certainly on a great circle, right? And then it comes around, and I'm kind of abusing the perspective there a little bit. So imagine that's a great circle, it looks pretty bad. But there's two ways to travel from A to B here. One is long, dark side of the moon, the other's the short one. But they're both geodesics. They are lines. So if you're on the sphere and you're a little bug, so let's see, so here I'm a little bug, got legs and stuff like this. And I'm walking at a constant rate. My velocity vector will not change for me. If I am walking in a straight line and I'm keeping my vector and I point my finger out and I just keep following that, I will walk a straight line.
Like if you had a compass. it
If
wouldn't
I had a
change.
compass, yes. And I would be walking a straight line. That's intrinsic. This little bug thinks he's walking in a straight line because it's like, I'm following the compass. Doing it. My velocity vector is in line with my travel. Right? So if I'm moving, and I'm moving in the direction of travel, that's a line. If I start to have a velocity vector that isn't in the line of travel, what am I doing?
Turning.
I'm turning. Yes.
Yeah.
So this little guy, so intrinsically, just the word intrinsic, intrinsically, I'm having trouble. Intrinsically, we think about straightness. Extrinsically, we see that little bug spinning around in a circle. So extrinsic geometry is about what happens when you're viewing the surface from afar. Intrinsic, and that's what we're mostly concerned about in this class, is what is it like to live on that surface? Is this feeling okay?
So you can walk on the edge of a circle in a straight line.
Yeah,
Intrinsically.
intrinsically.
And the other version,
Extrinsically.
you cannot.
Yeah, you're right. No matter how you move on the sphere, it is not a straight line
Okay.
from the outside perspective.
Okay.
Yes. Yeah, beautiful. There is some interesting stuff here. Lou brought up the fifth postulate, the parallel postulate. Let's just talk about this. We're going to hit this again harder later, but why not now, since Lou brought it up? So the fifth postulate said, if I have a line and a point off the line, then there is exactly one line through that point that doesn't intersect this. Do you remember that characterization of it? And that line is the one that's at a perfect right angle like that. Those two will never intersect. But what about on a sphere?
Intrinsically, no, they won't intersect.
Yeah, hold on. So we'll take this line here, right? Here's point P. Let's let the equator be our line.
Mm-hmm.
How many lines are there through here that don't intersect L?
None.
Exactly. Every line through P intersects L.
Huh.
Because the only one that wouldn't would be this little circle.
It's no issue,
But that's not a line.
because it's not on it.
It's not on a great circle. So think about
But
every great
intrinsically
circle
it's a
through
line.
P. What's that?
Intrinsically, it's a line.
Yes.
But what-
Intrinsically, a line, we have to only think of great circles. So every great circle through this point P has to intersect that line somewhere. In fact, in two places, right?
Yeah.
So we're already seeing a big change from Euclid's fifth postulate once we move to a sphere. In Euclid, on the plane, there's exactly one line. On a sphere, there are no lines that are parallel through a point. Yes.
So basically, what we could say is that no two great circles can be parallel to each other.
Yes,
Okay.
that is right.
That makes sense. But you're not defining them as parallel lines either. So
Right.
why would they not?
Well, I think parallel
What was-
probably is defined as they never meet, right?
Never intersect.
Never intersect. Yeah. That's the definition of parallel, I think, that probably.
But great
works best.
circles do intersect at one point.
Say that again?
Great circles do
Yes.
intersect.
So there are no parallel lines on a sphere, because lines are great circles,
From looking at it this way.
intrinsically. Living on the sphere.
No.
Okay, you and me, we're gonna walk to the North Pole from right. You stay over there. I'm gonna stay over here.
I'm in trouble.
We're gonna walk to the North Pole. Get your compass out. Will I meet you? I will meet you at
Yeah, at the North Pole.
at the North Pole.
Yeah.
So there's no way for us to walk on great circles.
Okay, but we live on a sphere, don't
Yep.
we? And we have parallel lines here on Earth. And that is an intrinsic observation. If
Where
you just said intrinsically, we cannot have that.
Where are the parallel lines on Earth?
I can make some for you right now.
Do it.
These desks are parallel to each other.
Well, these aren't lines,
Why says who?
because lines on a sphere are great circles. That was what that experiment was about,
Yeah.
right? Does that make sense? You
Yeah.
don't. Why are you hiding? You don't quit eclipsing yourself.
Eclipsing.
What's the problem? Let's talk.
I just don't have a good understanding of this. That's all. It's all good. I just need to sit with this some more.
No, we need to get through this, because if you're having an issue with this, it might be an issue.
Because you told me to think intrinsically in this class, right?
Yes.
And I'm thinking that if I was standing on Earth and I had two pieces of rope, that I could make them parallel to each other and they would never intersect. And if they were infinitely long, right? But if you were to think outside, then they would.
You've got two big. So here's Alexander.
Yeah.
Here's his piece of rope 1.
Mm-hmm.
Here's your piece of rope 2.
Okay, but you see, when you explain this to me right now, you're like explaining it from the outside of a sphere, not if you're living on the surface of it.
No, I'm drawing for Alexander on
Living
the
on
sphere. Living on the sphere.
Living on the
So
surface.
Alexander's got piece of rope 1, piece of rope 2. These are big fucking pieces, because this is like the Earth.
Yeah, they're
Right?
infinitely
So it's
long.
like the size of Colorado and Wyoming
Sure.
together. So you've got your two pieces of rope here, and you say to me, these are lines, and I'm going to extend them forever. Now, you're either extending them around the Earth, or you're pretending that straight things continue off of the Earth.
Sure, either way.
Well, if you continue them off the Earth, then that is an extrinsic idea, and you're thinking in planes, you're not thinking in spheres. So in spherical geometry, we let go of this idea of the plane, and we only work on here. Only on the sphere. So, okay, so you're like, okay, all right, whatever, sure. I've got my pieces of rope, I extend them infinitely. I've got this piece of rope, and it goes around here, and it goes around here. Are those lines? Those aren't lines.
Only one could potentially be a great circle, the other one would not.
Yeah, only one of these could potentially be a great circle, and the other one wouldn't. It'd be above it or below it. It's a different line of latitude. Right, so these are lines of latitude. The only line of latitude that's a line is the equator.
I understand this for sure.
Okay,
All right, you said something that triggered me, and it was that you can't have parallel lines on a sphere.
yeah.
But if
I wanted to trigger you.
But if
so
I'm
this is
living
good.
on the sphere relative to the size of however Earth, right? Then I can. Okay, so I can't make parallel lines with the definition of a line on a sphere.
There you go, and that's all we're saying.
Okay,
It's think definitions.
I can accept that.
Okay, good,
Yeah.
good. I see you accepting it.
I can accept that for sure.
Lou.
Is this like locality versus non-locality? Like locally, I'm here, and lines, and then like non-locally, not lines.
Those, yes, and I thought that's kind of what Alexander was thinking, that locally, I've got these two things, they'll never intersect. I agree. But to extend them infinitely, first off, isn't possible.
And that's not intrinsic. Locally is not intrinsic.
Exactly.
Okay.
Well, locally can be intrinsic, but these two things wouldn't be lines on Earth. These aren't lines. Well, one of them might be, if I kept on going, but the other one ain't.
And what is that?
One is a line, one is a circle.
And you said that wouldn't be
Right, 'cause it's, like,
intrinsically,
off the center
that would
point.
just be locally?
That
Or are they the same, sorry, I'm just trying to get the
yeah,
definition.
let's not think locally. But that it was just for a moment there.
Okay,
Yeah, I think it might get things. We got enough weird stuff going on. So this, you got a great circle. Any other line on the Earth is essentially a circle,
A level curve.
a level curve. Yep. Where were we?
I'm sorry.
No, that's what this class is for. Thank you for playing along.
We can move on now.
This is great. That's what we're here to discuss and figure it out, and it's weird stuff. I appreciate you being curious and asking. Thank you.
You're welcome.
I'll give you $10 later.
Let's go.
Give you 10 Memdex.
Hey, you know what? It's more than I have now.
Dr. T,
Yes, sir.
when we're thinking spherically, in spherical geometry, are we not allowed to think about unfolding the sphere when we think about whether something's a line or not a line?
Correct.
Okay.
Because, so think about how you know, when you do maps of the Earth, there's all sorts of ways to do that, and some of them are really weird. You know, you've got like the weird Mercator projections where they cut it up and lay it out. You can't, it is impossible to take a sphere and represent it without distortion flat. So every map of the Earth that you see that's flat, things are bigger than they actually are relative to other things. So this might be what it looks like on the map, whereas on the sphere, they're actually the same size, but I had to do some distortion to get it to look flat. And if you look at airline routes on a map, so if you are, you're gonna fly from Denver to
New York.
Boston, right?
Boston.
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 The flight paths don't look like that, do they?
No.
They look like that. Because that map is a distortion. And they're trying to represent a sphere. And this is actually a great circle that you're traveling on.
So we're traveling on a line.
Yes.
So are all flights taking great circles?
I think so.
And
I don't know. No. What?
Don't want fuel efficiency. I mean, sometimes they won't if they're trying to get to one place to another, but there's like a mountain range like ours.
Yeah,
that they take
yes.
deviations, but most of them will be.
You know a lot about this. Tell
I'm
me.
gonna go into air traffic control.
Damn, really?
Yes.
Wow,
That's
that's cool.
really hard job.
That sounds hard on your heart.
That sounds way more stressful
One
than
wrong
math
move.
Well, not
professor.
only that, but then my high school had like a STEM program that I was in, and we had to do air traffic controls with speed and location of the airplanes and determine how fast they had to come in to not crash with each other
Cool.
at a 3-degree angle, which is how they all descend. So
Did you have a simulator
Yeah.
also that you had to work with?
yeah.
Wow.
So cool.
It's like you're in high school. You're like, high school's not stressful enough.
Oh my god. Me and my group were the only ones out of the whole entire class that were able to get something that actually worked for one simulation, and there was like thousands
That's
of them.
impressive.
It
Wow.
was hard. We worked on it for 2 weeks just to figure out how to do it.
You ever want to give a talk on it?
I could.
That'd be cool.
Yeah.
I think that'd be a cool talk.
Okay.
All right, I'm
Right.
signing you up. Awesome. That's really cool. That's really cool, Penelope. Is there anything else that we want to talk about with this? I'm just making sure that I've said the stuff. Explain this to me. I was going to ask you this. In using the words extrinsic and intrinsic, why are flat earth folks so confused?
Oh, because they're only thinking extrinsically.
Yes.
Yeah.
Intrinsically, right? Because they're thinking like,
On the surface.
it looks
yeah.
flat.
Yeah.
It's locally flat.
It's locally flat.
So therefore it's always flat. You know it's not flat. You can't be an air traffic controller and a flat earther. Unless you're gonna fly him right into the ice wall. Or whatever. Sorry, I know way too much about that crap.
Sounds like someone's a flat earther. Just jokes.
It's kind of like weird science porn. Like, it's just like, what kind of twisted shit is it's dark web science.
Keep your friends close, but your enemies closer, right?
That's right.
Yeah.
That's right. What are these crazy? I saw a thing where there was a flat Earth guy, and some scientists took him to the North Pole because his whole thing was there's no such thing as a 24-hour sun, and they're like, bro, come with us. We'll pay for everything. They flew him up to the North Pole, and he's like, I'll be damned. The sun never sets. Look at that. And he's like broadcasting it, like streaming it live, and all the flat earthers are like, he's sold out. He's compromised. They gave him money to say this. And it's like,
The round earther lobbyists got to him.
Flat Earth Society
Even
for
if
life,
you look
baby.
at the shadows on Earth, and it makes a circle with the shadows. Even if you look at it, you're like, how?
yes,
So,
yes. Eratosthenes, back in Greece, proved the earth was round and figured its diameter based on shadows. And somehow we're where we're at. I mean, no wonder the world is the way it is. We can't even accept the earth is round.
Don't put them in this class.
Yeah. So I have a little. Let's do a little bit here. We've only got about 20 minutes left, but can we do some group work? Just a little touch. Yeah, let's do some group work. So you three, you two, you two. Sound good? Cool. We'll mix it up. So here's what I'd like you. Let me say a little bit, and then set you free. And I want you to mostly think about some definitions. That's all. So to come up with a definition in your group. So we're going to talk about angles now. Because eventually we're going to look at triangles on a sphere and how do you find the area of a triangle on a sphere? What are the sum of the angles? All sorts of cool things like that. So we just want to understand angle first. So there's 3 ways to consider angles. And we talked about this, so let's summarize it just a little bit. We did talk about this briefly. So the first one is this dynamic motion-based action-based idea. And that is, I've got a point, an array, and I pivot that. So there's this idea of motion, moving this ray to that ray. And the angle is what happened there. The angle was created by the motion, pivoting motion. Does that sound good? So we can think of an angle as something that results from motion. We can also think of an angle as just a measure. And in that sense, what we would do is, we have this thing that we call an angle, and we can think of the measure as the portion, well, we think of the point of the angle being at the center of the circle. I draw a circle around here, and I think about either the distance of the circle between those two pieces, so the distance equals the measure, or I can also think of it as the ratio of this arc to the whole arc. Couple ways to think of it. So that this is radian measure, right? Radian measure is where you have the unit circle. And let me just kind of really quickly say something about that, because you know this. A lot of people remember the unit circle, right? If this is radius 1, what's the full circumference?
2 pi.
2 pi, right? So 2 pi equals the full distance around. So we say that this is 180 degrees is 2 pi, or 360 degrees is 2 pi.
I was like,
Yeah, I know. I got pulled out of the nosedive. Penelope was like, no, you look out, you're too close to the ground. I heard her. And then we just look at the ratios of that. So we say the full distance around is 360, so halfway pi radians is 180 degrees, there's pi over 2 is 90, and so forth. And it's just it's literally the distance on that unit circle is radian measure. So we've got motion, just simply looking at the portion of an arc that subtends the angle. Subtend is a really good word. Subtends the angle. And then we have the last one. It's just a shape. It's just a shape. Ouch. It's a pointy shape. Careful. That's an angle. Ouch. Wedge. Piece of pie. Pac-Man mouth. Whatever. So we've got these 3 ways. So in the shape is 2 intersecting lines, really. 2 intersecting lines. So those are really the 3 ways. So what I would like you to do in your groups is come up with a way to explain congruent angles in ideally these 3 ways. How would you test for congruence? What does congruence mean? Sameness. So what I'd like you to do in your group is define congruent angles. And this isn't a very hard thing to do, really. Just think about it a little bit in each interpretation.
isn't it the same? I should talk to my group.
Well, talk to those guys about it.
Isn't it kind of the same, you know? Like a congruent angle, if you just define a congruent angle as 2 angles that are
Yeah.
equal.
So if we have 2
Then-
intersecting lines, I think that's
Okay, alright, oh no, I can do this, okay, so on the like the unit circle way, it's equal rotations, or like equal distance traveled from the start.
with the same measure of distance.
That would be like the same, right, cause it doesn't matter if you travel in the negative or positive direction, the distance is the same, right?
We have 2 intersecting
Alright,
lines
we'll
with
go
the
with
same
that one.
measure.
For that,
I mean, we can use that.
and then there's the other way, which is,
Or if we have 2
wait, there's
pairs,
like 2
there's
ways,
no
2 ways, right, the shape.
2 lines on top of each other and then
Yes.
Okay, well, like in
Same
simplest form, like in the
dynamic
one,
ranges
like the very first where you just like it's the distance between 2
at the
like
same measure.
non-congruent or non-parallel lines.
Then we get the same.
2 intersecting lines, I guess.
Like those
Then it's
angles are
just,
gonna be the same, I'm doing the same thing twice.
Angle.
What do we call that in like high school geometry?
This is
Like a little flexes.
really making
Like if you
shapes.
smell like
What's going on over here? Oh, tic-tac-toe.
Do you know why I was laughing earlier?
Sure.
Because you were like,
Yeah.
I can't even register
that guy
that
was
word.
just staring at me over the computer.
Yeah, I've never heard that before.
I don't have any
Yeah.
Like, okay, I mean, I've heard the words independently from each other, but not like, I'm talking like a geometrical rule.
That's why I was laughing.
Okay, gotcha. I thought you were mostly laughing
Maybe you're
at how
right.
ridiculous it was
That-
that I actually had
That
to
was
say
part of it,
it
because
all.
it was
Yes.
ridiculous, and I thought it was ridiculous.
Yes.
I was like,
One of the lines.
Yeah.
the way it's speaking over my computer.
What is that?
I don't.
Yeah,
Is that yours?
No.
What's this thing?
You're not British, but you speak British
Wait,
English, so that's why I was.
oh wait, that.
It's not British English.
I thought it was talking about Evan, and I was like, why was that?
That weird little
Yeah.
paperclip guy or whatever.
No, I
Flippy.
wish you could see it, because the reason why I was laughing earlier in class is because it's just like.
I'm
I
doing
got
over the
nothing else, guys.
computer.
I can't listen to
He's done enough.
Yeah.
Yeah,
Enough confusion.
Oh,
Maybe you can do something, huh? This is beautiful
say it again?
paper. Wow, that is
What is
gorgeous.
that for?
Yeah, look at these circles.
I wouldn't expect nothing less than such a classy man.
Right?
I know,
I
right?
know.
Like, this bro
Dude,
is
that's
like,
actually so
Yes.
he's
Tell me
always
about all
styled
my
I'm
friends
telling you.
completely.
For their like.
Me and I was just telling Abraham how we
Like
should start
class, they
dressing
did
like
the
Joshua
popsicle
and maybe
thing from, like,
develop his
kindergarten.
powers of like astutness.
Why can't we do that?
Is that where
No,
it's coming
that
from?
made,
I
that
must
made
feel
me
like
mad.
it's
If I'm trying to
Yeah,
like get
it's
out of
probably
here
a
and I'm trying to
power
get out,
base.
don't make me do the
But you know, look good, feel good,
Yeah,
right?
we're all
Absolutely.
trying to get out of here. This
That's
is
not
our
fair.
this is
Well,
our
next
year.
You're playing good.
This is like my work outfit. This
Yeah.
is like when I go home, I get casual.
Yeah. What does casual look like? Yeah.
Just like a sack with a rope.
Oh no, it's the it's your what's the gardening outfit that you got? What I don't want to call it a dress, but it's
Oh yeah,
it's
my
a dress.
yeah. My kaftan.
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 No kaftan.
There's a term in like high school geometry.
Congruent?
No.
Oh, interior, opposite
Yeah.
angles?
Yes, that's totally what it is. It's interior opposite angles.
Is that you remember that from somewhere?
Yeah, from like high school geometry.
Yeah.
Yeah. It's like when you have two intersecting points, right, and they create like a near angle for the same, the on either side.
Exactly.
Yeah.
It's like the vertical angle theorem. It literally is
It's
that
like the
vertical
same
angle
thing,
theorem,
yeah.
right? That
Yeah.
you're going to memorize. But yeah.
I'm gonna memorize mine down for you.
So,
By next
what
Monday.
for what? Everything?
That's insane.
But yeah.
I'm sorry.
Yeah, if you miss, it's a point award.
One for one. Yes, sir.
Right.
No Joshuaisms.
You make it sound any different.
Speaking Joshuese.
It's true, they do speak slang English from this country.
If one line's in motion from the pivot point, and the motion is the same measure, duration,
Yes, I understood.
angle.
I knew what you meant.
And measure.
Just get in line. Smack your hands with a stick.
Get the ruler going. Alright, so we can define these. We're good. We're chill.
How we doing here?
I think
Think we got something?
Yeah.
Chocolate
So
cheese.
basically, well, I kinda started out by saying that we have
Cheese
two
and,
lines
like-
that are like laying on the top of one another.
It's like when you're like,
And
you like can't stop smiling. It's like a natural, it's like a very natural smile.
from that pivot line.
No, you're smiling. You are smiling. But cheesing is when you're like extra smiling. It's like an extra effort that you don't have to inherently make because of another end.
So are you talking about this is the measured version of it?
Yeah.
Yeah.
It sounded like you were talking about
So it's like
motion.
laughing isn't cheesing, but
Well,
if you're
yeah,
like
that's what
cheesing
I
while you're
kind of try
laughing.
to put all the rules in, so if we start like the lines
Yeah,
on
yeah,
top of
yeah,
each
yeah.
other and they have
That's
a
like,
pivot point.
I feel like when
And
It's
we
one of
measure
those.
that
It's like okay. It's like
and it's like
what do you call them?
the
You
motion
babes?
of
You
it,
call
but
them
if the
babes. It's like you know when
measure
you're
after
like
that
punch
motion
it,
is
like
like
she's making you cheese.
cheese.
Just like remind yourself, just like cheesing.
I agree with that. I agree with that. How could we do it sticking to only motion?
On the motion?
Yes.
Without the measure part.
Okay.
Yeah, you're like
which gets a little more
So
painful.
an
You want us to do
overwhelming
it?
amount of
I
passion.
don't like, I mean, what you did is great, and
Okay.
it's a good definition,
It's
but
okay to tease
to
everyone.
make it a little more
Yeah, yeah.
challenging.
Or you know,
Well,
Wait,
you know,
almost
like
In
How did
each,
you find out
really
like,
terrible
scenario.
happens in your life and you can't stop the
Okay.
tears
Right,
from coming
so we'll
out.
say
It's
two
like the
angles,
exact
two
opposite.
angles
But
are
like,
equivalent,
did they,
But like
if,
the happy
like,
version.
like the
Yeah.
person
and I'm thinking only as the motion-based idea.
Yeah,
How could I-
yeah, like opposite.
how could I
like
discern
opposite anti
That and that are, let's say this, and let me make it a little less obvious. And I move that, and I move that. How do I know those aren't congruent with motion? Yeah, because these two don't look congruent, right? We would hope these weren't congruent. Like thinking only in terms of the motion or thinking in terms of, so the measure part, I think you got,
Yes.
right? Because that's pretty straightforward. We put a circle here, we measure,
Yes.
literally measure it. Get our protractor out and measure it.
Any that you
But what about just that motion based?
calculate results multiple.
Or what about the shape based?
I actually don't think any of the concepts are calculated that hard.
How would we know two angles are congruent?
Are you talking about like the,
Yeah, it's fine.
I guess that's measuring it again.
Yeah, so try to avoid, yes, and your brain wants to go to measuring. So like maybe work
Is
with
it like
this
the
one.
properties of a
Yeah, just
triangle and a
so
square that we're trying to?
Oh, I'm not even sure what you mean by that, but I like where you're going.
So like,
And even though they're all retaken.
if we have a parallelogram,
So if you
Right.
fail it, you just retake it.
then we know this side is equal to this
The
side.
reductor side,
yeah.
It's like something like that. I don't know all the rules, but that are like for
Well, you know,
angles, like this angle
Yes.
is equal to this angle and this angle. Is it that one?
Yeah,
Yeah, like maybe.
but we're falling back, I think.
Yeah.
Yeah, maybe, yeah, kind of.
Okay.
But those would come from like
Not a bad-
the vertical angle theorem that we're
Okay.
gonna learn. So like, what if this, so if the only way I can say, I say this is an angle.
Yeah, I got
And
you.
it's an angle because it actually is part of two intersecting lines.
Sorry,
How can I say that these guys
You need to text
in
me.
this angle and
This
this
is
angle are not congruent? Using the intersecting lines idea.
Okay.
Whoa, use
Is
something.
it something like the parallel theorem that we need to?
I don't, no, you're getting too
Yeah, the
fancy.
DI
Think
method,
more
the
practically.
tabular method.
The only thing you can, so
With the
the
bounds,
only
like
thing
if
you
it's
can
a
do is
definite integral.
extend these lines.
You don't need to use.
No, that's an
you need to use
angle
something.
because
Oh, you
it's
have, like,
these two
integral as
lines
bounds.
intersecting,
Oh,
right?
that's a crazy integral you have to solve.
Why is that
And
angle
you would
not the same as that angle?
Yes.
Yeah.
Only thinking about intersecting lines. Or what would make them the
So
same
that actually is devastating though.
if I extend
Like
it.
if I had C here.
Maybe think about isometry.
Think about all the eras.
So think about isometry.
Like middle school.
So what did you think, since you're engaging with everyone,
You'll get it.
what did you think about my,
Wait, so it's
on a radial method definition, radial,
So which one are we looking
on like
at?
the unit circle, like pi over 2.
Okay,
that.
cool. Yeah.
I'm thinking it as distance traveled from one point to another, and if
So
you
what do you have
move
to do with the translation, like
Well, I
the
guess-
rotation?
on a unit circle, the pi is gonna try to be like,
Yeah, let's stick to unit circle. Yeah, that sounds good.
but if you were to travel clockwise or counterclockwise, right, like the distance traveled is the same,
Yes.
right? And so like a congruency would be just like distance travel has to be equal to each other,
Yes.
and that's how I defined it.
I like that one.
stopped there.
No, this
Yeah,
works
I
for me.
didn't really go
Yeah.
any further.
Yeah, they're,
Half turn center.
yeah, I agree with that.
Yeah,
That sounds good.
yeah, it's like right triangles,
Do that also.
you know?
Exactly.
Yeah.
Yes. So now I would, and you guys have just a short window
You challenging me?
challenging you guys. So what if I use the definition that this is an angle
Uh-huh.
You're
because
positive that this.
it's actually the intersection of two lines.
Uh-huh.
It's the space between the intersection of two lines.
It means on a sphere, those lines rotated at certain
No,
distance.
don't think spheres or planes. We're gonna think in a way that's general to all those, all the places we'll think about. Cause we're gonna think about planes and
Okay.
spheres and other weird places.
Okay.
So here I got two angles. Angle because it's two lines intersecting. Angle because it's two lines intersecting.
Yep.
How can I determine congruence between two angles using that idea? That an angle is only an angle because I can extend the sharp point to two intersecting lines. How can I use that idea to define congruence? And I'm gonna give you a hint. Use this word.
Geometry.
It's a reflective, what do you call it? No, it's like literally a reflective symmetry, right?
Well, maybe I don't know what you mean.
A reflection symmetry, because if you have that,
That angle on the other imaginary lines are the same, right?
So what do you mean?
You want me to draw something?
Yeah, I want you to draw
I
something.
thought you were saying, tell me more.
Well, I am.
Sure, yeah, well, okay,
Show me.
I'm actually asking you.
Okay.
Cause this could be, is this the same?
By the vertical angle theorem it is, and we'll prove that. We don't know that yet.
So I can assume that it's the same,
Man, I don't think we can assume that yet,
alright.
because we'll prove that later.
Not the same, guys.
Okay?
I don't think it
But what were you thinking? So
Well-
if it was, how would that help?
No. Actually, I was like, I kinda wanted to say like the way these, I don't know, let me think about some more.
Okay.
Let me think
But
about
like,
some more.
it's just like-
Because I feel like on a sphere, you could just think like where it lies on a great circle, but it's not on a sphere. So like,
Necessarily.
I mean, this counts as isometry, but isn't it just transformation symmetry?
Oh! Yes, say more. Say more. Let's let
I
Abraham.
mean, like you transfer, like if you keep going, it's gonna end up at the same spot. It's also gonna end up at the opposite of it.
What I'm confused about is like, I understand what you all done from each of these groups.
You can try.
How can we
No,
translate?
Yeah, because you're saying good stuff. I need you to write. Come on, I'll come up with you. We'll be safe.
okay, hold on, let me.
I'll take your hand if we need to.
I'm
Let's go
saying
together.
that transformation
Reflection is the same.
symmetry is that even if it starts at this point, it's gonna end up at this point, given it that it's the same, it's following these lines. Given it's the
Yes.
same.
Yes.
And it's gonna end up
Oh,
at
you
the
think
same spot.
translational symmetry, or what do you mean by so what do you mean exactly?
Like rotating.
Oh.
Explaining is the
Okay,
same.
I like that.
Wait.
I like that. That's definitely part of it. Yes. So how could I tell that these two are not congruent using your idea? Let's see, you got it. You really got it.
I have an idea.
Come in and sit, come on up.
If you have an isometry.
I can't hear you. Can you come up here?
Alright, okay, so an isometry is a transformation that preserves distance and angle.
Correct.
Correct, right? So if you like close this and then transformed it, it would preserve its distance and angle.
Yes.
Same as well here, and if you measure this distance, you would know that x does not equal y, so therefore these are not congruent angles.
But then you're measuring.
Yeah, you are measuring.
Alright,
So
so you
let's
can't
get-
measure. That's okay, no, I didn't like measuring.
I know, that's what I keep on going back to. I was like, okay, that don't work, I'm measuring again.
Let's get this together. We can all do this together.
I'm gonna,
This is good. So, got this angle, and I got this angle. Let's get all this stuff out of the way. These are angles because they're a portion of space resulting from two intersecting lines. How could I show that either this is equivalent to this or this isn't equivalent to this using the idea of isometry? What is isometry? Translation,
transformation
Ro-
with
rotation.
preserving its definition.
Yes, it preserves the angle, so it would preserve this. It would preserve. We don't really have lengths because everything's infinitely long in a way, right? We just imagine these guys go on forever and ever, so we don't have to worry about lengths.
So if you can make that's why I was saying earlier, like if you are able to successfully complete reflection symmetry, then you would have, I guess then those would only be congruent to each other, not necessarily.
Well, let me make this. Imagine this one is on a piece of tracing paper that I can slide around. Okay.
Well, couldn't you just like move it over onto the other one and have one of the lines line up with the other one?
Yes, yes. So, using this idea, if there's an isometry of these two lines onto these two lines, if there is a translation, rotation, flip, whatever, we don't even need flips really, right? Because these are kind of, these are reflection symmetric in lots of ways. So, if I just have an isometry that moves, translates, first off, you translate the intersection, right? So I do a translation, and then I do a rotation. And if I can get this to match up with that, they are congruent.
Wait, they're congruent as in that one is congruent with that one,
Yes.
not with the other. Is that what the question was?
Yeah.
Not like,
So yeah, the question was, how can I discern if that angle and that angle are
are
congruent?
equal to each other, yeah.
And the answer is if there's an isometry of these two lines onto these two lines.
Is there?
Not here. Here there isn't, because I would have to change the angles, right? This one I would have to kind of like change space to get it to land onto this. But if I just took this guy over here, and that's beta, and assuming that take this, bring it over here, translate it so that this point lands here, and then rotate it, they would mesh up perfectly. So if there's an isometry of this figure onto this figure, then those angles are congruent. And does that make sense?
I was trying to prove it without lifting it up.
Yeah. So we could just, it's just sliding.
Mm-hmm.
Yeah, sliding. Kayla and Lou, does that make sense? Kayla, you said it, so it's like, yeah, cool. All right, good. Yeah, it's fun. Good stuff. That's all I wanted to do today. What is your task?
To memorize the vertical angle theorem, no, yeah.
Yes, that's one of the tasks.
And also define symmetry, isometry, and geodesic, and, there's one more thing.
Damn,
Oh, intrinsic and
you got
extrinsic.
the list. There we go. And
And read the pages.
36 to 36.
32 to, 40.
32 to 40,
9 pages.
9 pages. There's probably pictures. You do not need to prove, there's pictures. You do not need to prove the vertical angle theorem. We're going to do that together. And hopefully we'll have the other quarter of our class here with us.
And I'm gonna get more points on the quiz.
I appreciate you